Welcome to the course on design of power electronic converters. So, we were in the module on power semiconductor devices, and prior to this we had discussed diodes and also MOSFETs. Now, another important semiconductor device which is widely used in power electronic converters is your IGBTs. So, now we will be looking into IGBTs. This is the symbol of IGBT you might be already familiar with. This is like the symbol of BJT, but here you observe that there is another line which is drawn. BJT has only one line in it, and like your BJT, it has got these your collectors and emitters, but it does not have the base but the gate. Okay, like your MOSFET, it also has the gate. And this is the physical structure of the IGBT. Okay, it consists of this N plus region which is connected to your emitter, and then in between it has the P plus region, and then further it has that N minus drift region and then P plus region, and that is connected to your collector. And over here on the gate side it also has that oxide layer, and it is similar to the MOSFET. So, now what we observe from here is that on the gate side it is like your MOSFET on the gate side. And on this collector emitter side it is like the BJT. So, IGBT is actually a combination of MOSFET and BJT, you can say like that. And because of it, what happens is that your switching frequency Fs for IGBT, this is greater than BJT, it is greater than BJT but is less than MOSFET. And that is the reason your IGBT became very popular, because when people were earlier they used to use your silicon BJTs, the problem that used to happen was that the switching frequencies were not very high, whereas your BJTs they can carry lot of current, their power levels that they can withstand it used to be much higher for power BJTs. But for MOSFETs on the other hand, the power handling capacity was much lesser because they were majority carrier devices, and because of being majority carrier devices, the RDS on used to be very high, and so your power level for which they can be used became limited. And your switching frequencies, although for MOSFETs were very high, but BJT power BJTs they could be used for much higher power levels, but their switching frequencies were not so high, and moreover they are current control devices BJTs. So, that's the control is little bit more involved in case of BJT, whereas MOSFET controlling was much simpler because it was voltage control device. So, this IGBT is turned out to be in between your BJT and MOSFET. It could be switched higher than BJTs, lesser than MOSFETs, and power handling capacities were also somewhere between your MOSFET and BJT. Lower than BJT power BJTs they can handle, but higher than MOSFETs they can handle, and that is why your IGBTs became very popular and is used a lot in your medium power applications, especially for your DC to AC applications. So, as I told you, another important thing that you should remember is that these are minority carrier. Minority carriers, they also participate in the conduction of through IGBT, and that lowers the on-state voltage drop in your IGBT. So, your collector to emitter, this on-state voltage drop is smaller than MOSFETs. Now, these are some of the pictures of your IGBT. This is a discrete IGBT. Okay, you can see the 3 legs that are there, collector, emitter and gate. And then IGBTs are also available in the module form, integrated module form. So, this is one leg of an IGBT, this is by Infineon, and this is also 2 IGBTs together. Okay. This is another module, and these are your those 3 terminals like this over here, 3 terminals that you can see, and there you have these 2 gate emitter terminals as well. So, these are your gate and emitter terminals for 2 of those IGBTs, and this is your collector emitter for one of them, in the collector emitter for other one. So, those are the ones that you can see here, collector, emitter, collector, and this is your another emitter, like that. Okay. Further, what is possible to do is that having one entire inverter, a 3-phase inverter can be there inside one module, and that is what this picture is showing. Okay. This is one integrated module having 6 IGBTs and 6 antiparallel diodes inside it. Okay. And this is a picture of an IGBT module of this 3-phase inverter only, but of further higher current levels. Okay. So, that is why you see that this is bigger than this module. And one more thing that you should remember is that in case of MOSFETs, we said that there is a body diode, and so MOSFETs, without doing any additional connection, they are able to carry the current in the opposite direction. But in case of IGBTs, it is not so. So, what people do is that they connect an additional antiparallel diode, and that is what is shown here. This additional antiparallel diode is shown here, which is connected over here between the collector and emitter. So, this is something you have to do additionally, and most of the manufacturers, if they are making IGBTs with antiparallel diodes, then they will be also providing you the characteristics of the diode. And there are IGBTs also made without antiparallel diodes, although they are little less in use, because most of the power electronic circuits that we see, they have the antiparallel diode requirement with the IGBT. So, that is how most of them are manufactured. So, that is why it is important to look into the data sheet whether the antiparallel diode is present, is provided by the manufacturer or not, or is it just a simple IGBT. Then I wanted to show you what is inside these modules. Okay, how do they look inside if you happen to open those integrated modules. So, this is the module by Semicron. This is Semix 3, that is how they have named it, and you can see here these are 2 big terminals coming out here and on this side, and then they have provided what how does it look inside. Okay. So, here you can see that these are those 6 chips of the IGBTs that are provided, and also your 6 of these diode chips that are also given. Okay. This is for IGBT and this is for the diode. And then there is, it is like a small PCB inside the module. There are all these connections are formed here. You can see all these copper traces over here. These copper traces, you can see it Okay, so like a PCB inside, and then you can also see these bond wires. Okay, that also you can see interconnecting wires are there inside them. So they will have their own your inductances associated with it. And then further, this is your DC terminals that are given on this side, and these AC terminals which are brought on the other side. Now, what are the important parasitic elements associated with your IGBTs? We will be discussing only the important ones. So, this is your IGBT, and this is your collector, emitter and gate terminal, and then you have capacitances associated here between the collector and emitter, which you can call it as CCE. Then there is capacitance between these two, which is your gate to collector capacitance, and then there is capacitance between gate and emitter, which is your CGE. Okay. So, this is similar to what we had seen in case of MOSFET also. So, the turn on and turn off characteristics of IGBT is very similar to MOSFET. So, they like over there 3 capacitances played a role in your turning on and turning off, and similarly it is so in your IGBTs also. So, here your this input capacitance your CIES, like in case of your MOSFET, it is the sum of your gate emitter plus your gate to collector capacitance, and your output capacitance COES, this is sum of your gate to collector plus your collector to emitter capacitance. And then there is this reverse transfer capacitance, which is equal to your gate to collector capacitance. And the origin of this is inside this physical structure, in between these different layers you have these 3 capacitances. This is not something any physical capacitance, I mean a discrete capacitance which you can see outside the MOSFET. These are capacitances, parasitic capacitances, because of this internal physical structure of the MOSFET. Now, let us look into the VI characteristics. So, this is your characteristics between your IC collector current and your collector to emitter voltage. So, this is your collector to emitter voltage, and here this is your gate to emitter voltage, which we can apply, and this is your the current that flows through is the collector current IC. Now, what we observe here is that as your this gate to emitter voltage, this increases, then and it becomes above the threshold voltage, then the IGBT starts to conduct, and after some times this current, this collector current becomes fixed, becomes constant. Okay. So, this region in which it is happening like this, where you can see both the collector to emitter voltage and your collector current, they are both high together simultaneously. That is your called as the active region. This region is your active region, and below the threshold voltage, when gate emitter voltage over here is below the threshold voltage. So, then the IGBT is not carrying any current, it is not conducting, and it can block great amount of voltages. So, that is your breakdown voltage. Collector emitter can block voltage which is positive with respect to the emitter. So, that is it is in the cutoff state or the forward blocking characteristics, you can say that. And then if that voltage becomes greater than the breakdown voltage, then of course breakdown is going to happen. And if we keep on further increasing your gate to emitter voltage, then a level comes where you can see that the collector current can increase to very high levels, and in that case it is going to be only limited by the external circuit, means whatever circuitry which is additional to it, which is connected to the IGBT. Okay, so that region is called as your saturation region. So, here this is your saturation region, but for that the amount of gate emitter voltage that we have to apply should be sufficient enough. So, from here what we observe is that if we change this VGE, then we can make it go from your cutoff to active to saturation. So, that is why this is also a voltage control device. And now let us look into this transfer characteristics. So, this is a graph between your gate to emitter voltage, this gate to emitter voltage, and the collector current IC. And as I have explained you, what you see is that before this threshold voltage is reached for this gate to emitter region, there is no current, it is in the blocking state, it does not carry any current. After that this collector current increases, and it increases very sharply. So, there is a slope associated with it, there is this slope, and this slope is then given by this your transconductance, the forward transconductance. So, this is similar to again MOSFET. MOSFET we also had the same term, and this is your delta IC by your delta VGE. Now, let us look into the switching characteristics of IGBT. As I have already told you, the switching characteristics of IGBT is very similar to your MOSFET, and so the way it is studied is also very similar to MOSFET. So, the switching I mean the circuit that we can use to study the switching characteristics will be like this. You can have this kind of an IGBT with antiparallel diode, and that diode this IGBT can be turned off by applying a opposite voltage in the gate to emitter area. So, emitter is made positive with respect to gate. So, this is turned off. So, that means this is blocking and this is not going to conduct. So, it is only the antiparallel diode which is what we will be using for studying the switching characteristics of this IGBT, okay, this lower IGBT. So, this is your device under test, many times it is also written as your DUT. Okay. So, then what happens is that as you provide gate pulse to it, okay, that means this is the high state over here. As we provide a gate pulse to it, positive gate pulse, then it turns on, it starts to conduct, and then current flows through this from here through this inductor. And when it is turned off, that means we apply negative voltage between gate and emitter. At that time this current freewheels and flows through this antiparallel diode. And what we do here, there is a driver circuit which we can represent as like this pulsed voltage source, which is giving your VG pulses, and the maximum it provides is capital VG, and here some, let us say, some negative voltage is also provided. Then in between there is a gate resistor RG, and through that this gate emitter region your gets charged and discharged. Okay, and this part is your gate emitter voltage VGE, which we will be seeing how it changes as turn on and turn off happens. And if we see the ideal current and voltage waveform, so this is your IL, it increases while the switch is on, slightly increases if it is heavily inductive. And at that time ideally collector emitter voltage is 0, and at that time this collector current is equal to your IL, and after that as the device is turned off, it blocks this voltage VDC, and at that time the current is 0. So, over here is this turn off happening, and over here is this turn on happening. So, this is your turn on and this is your turn off. Okay, so these are the regions that we have to look into it, that what happens to study the switching characteristics. So, let us look into the switching characteristics. So, before turn on, let us say a negative voltage is applied in the gate emitter. Okay. So, this is your 0 over here. So, a negative voltage is applied, negative voltage is there before the IGBT is given any gate pulse. Then as it is given gate pulse, this negative voltage starts to reduce and then it increases and then it reaches to a certain point. While that period, what we observe is that your this collector current is 0 and this collector emitter voltage is not changing. So, before turn on, what is the voltage over here? So, this is equal to your VDC, this is the voltage it is blocking, okay, and this current is 0 over here, and so then there is no change. So, this part we can call it as the delay time, so TD on, and till here what it reaches is the threshold voltage, we call it as VTH. So, this is your threshold voltage line. After that what happens is that your this current increases and it may actually shoot up, it will have an overshoot, and during this time this gate to emitter voltage also increases and there is no change in the collector emitter voltage. So, this is your associated with the rise in current. So, this we can call it as your TRI, rise in current, and this part your IGBT turn on is associated with diode turn off. So, this is your reverse recovery time of the diode and this is actually your reverse recovery current of the diode. This is like how we have seen in case of MOSFET as well, and by this time it actually reaches this gate to emitter voltage, it reaches to the Miller voltage, we can call it as VGE Miller, or PL it is denoted by several times. And then after this TRI interval, what happens is that this Miller period is there, and during this Miller period the gate to emitter voltage it does not change, but this VDS on this collector to emitter voltage that decreases, okay, during this Miller period. So, this we can name it as the fall time of the voltage TFV. After the Miller period is over, what happens, whatever is the rest of the voltage, the difference between your Miller voltage and this voltage VG which is applied by the driver, that this gate to emitter region that makes it over, and so over here this reaches to the final on state voltage drop of the IGBT, which is your VCE on, you can write it. And here by this time this current has already reached to its steady state or the conduction current, which is your IL. So, now what we see here is that by this time the device is on. Okay. So, this your turn on time T on, this is then can be written as the sum of TD on plus your TRI plus TFV. The sum of all these three is your T on. So, we saw that this is similar to MOSFET, how the MOSFET turn on happens. Now, if we look into the IGBT turn off, then what we see is that is also similar to MOSFET. First, the voltage reaches to the Miller voltage, and at that time almost there is no change in the voltage and current. So, this is your TD off, the delay during the off time. And then during the Miller period, what happens is that first the voltage builds up and there may be overshoot because of stray inductances, and the current does not change at that time. And then after that from the Miller voltage it goes to the threshold voltage, and during that time the voltage is almost settled back to your VDC, the blocking voltage, but the current there is a significant decrease. Now, in case of MOSFET we had seen that it almost becomes close to your leakage current, but here in case of IGBT this does not happen. There is some significant current which is left over here, and that further goes to the leakage current, while this gate to emitter voltage goes from your threshold voltage over here to the actual blocking negative voltage. Okay, means in the blocking state whatever is the negative voltage we apply to the gate to emitter, and this current is your tail current. And this is what makes the turn off process of IGBT slower than that of MOSFET. Okay, so that is why your IGBTs are they switch at lesser frequencies than that of MOSFETs because of this tail current. And why do we have these tail currents? Because you know that is not IGBT is not a majority carrier device. Both the types of carriers, your holes and electrons, they both participate in the conduction. So, while it has to be turned off, they both have to be removed. So, this intervals, this is your rising interval for the voltage. So, TRV we can name it as, and this whole of it is your fall in current TFI, we can name it like that. So, the sum of these three, your TD off and your rise in voltage and fall in current, these three together they form your turn off time of the IGBT. Okay, so, we saw that your switching characteristics of MOSFET and IGBT are similar except for the tail current. That IGBT has got a tail current, and that is what makes it a slower device than MOSFET. Next, what are the terms in the data sheets which are associated with switching? Your gate charge QG, then gate to emitter charge, then the Miller charge, gate to collector, then the turn on delay time, this we just discussed now, the rise time TR. So, this TR I have told this before also, this is your sum of your rise time of the current plus the fall time of the voltage TRI plus TFV. And then this is your turn off delay, and then is your TF associated with the fall of the current during turn off. So, what are the key points of this lecture? Three parasitic capacitances are important, they play important role in the turn on and turn off of the IGBT. and the voltage, gate to emitter voltage has to be above threshold voltage for it to turn on, and it is a voltage control device like MOSFET, and turn on and turn off is similar to MOSFET, but there is tail current in IGBT which is not present in MOSFETs, and which makes IGBT relatively slower device than MOSFET. Thank you.